All right. Well, thanks for having me, guys. And just like to thank everybody who's been involved in setting up BSides Manchester and making it happen. It's really, really quite a pleasure to be here. And I'd also like to thank Dom and Hacker Fantastic for doing a superb talk on zero sleep. I'm this guy. I'm Steve Lord. For that, I can only apologize. I have no slides. And the reason I have no slides is not because I'm unprepared. I mean, I am unprepared. Not just for this talk, but just in general. It's because I'm going to talk about hardware hacking. It's a very different type of hardware hacking to, say, the talk you saw earlier. And the talk that I want to talk about is, the thing I want to talk about is actually building your own hardware for hardware hacking. So it's great to pull things apart, but actually building something yourself from the ground up is quite a different way of looking at things. And you learn a lot in that process. And for a lot of people, the idea of building your own general purpose computation device from scratch with a printed circuit board and everything else is quite scary. But in actual fact, it's not that hard. In fact, I can do it, so you can do it. I want to talk a little bit about a thing called the Minimalist Electronic Learner, or MEL. Now, the MEL is a device that I'm currently building. The goal of the MEL is to provide a general purpose computation device with a few parts that anyone can put together. It's not exactly leading edge technology. It's got 8K of storage space, small amount of RAM in the order of a few bytes, but it's only got about 8 parts, and it's all through hole, which means that anybody who's never soldered it before can pick it up, solder it together, and start using it. But this talk isn't about the MEL. This is the talk really about the thing before the MEL, because the MEL is a general purpose hardware hacking device. And this is a specific application of the prototype. Now, I have a few things with me today that I was hoping to show you, but I appear to have left some of the parts at home. So instead, I'll focus on the thing that I'm going to show you, which is the Hidiot. Now, the Hidiot is a human interface device I/O toolkit. And if you imagine the MEL is kind of the finished general purpose hardware hacking thing, the Hidiot is a specific application of the MEL. And hopefully, if I pop this under there, you should be able to see. I'll try turning that around. See if we get that right. Nope. We'll try again. Hey, bueno. All right. So the HID-IO toolkit is a device that is a general purpose human interface device USB hacking tool built from the ground up. The idea is that it will simulate any slow speed USB device. Pretty much. It also, just by the fact of the technology that's used, happens to be completely and totally compatible with certain classes of USB device. So it's totally compatible with the Adafruit Trinket, the DigiSpark, and the Tynosaur. So let me have a look and see if I can bring up some stuff about the components on here. Nope, that's not right. That's not right. That's also not right. Bear with me. Because I can't see up there, it's a bit hard for me to walk through. Okay. So, up on the top of this thing, we have, going down from the middle of the top to the right, there's a set of holes. That's mostly decorative, but it also will work as a way of expanding the Hidiot. So if you wanted to go and interface the Hidiot with another microcontroller such as the ESP8266 that comes with Wi-Fi built in, so that you could create a head device, like a keyboard, that could be remotely controlled over Wi-Fi, you could do it with this. At the top, next to it, you can see there's a row of 8 silver things with a black thing in the middle. That is the core of both the Hidiot and the MEL, and that is the AT-Tiny85. Now, the AT-Tiny85 is a microcontroller made by Atmel, and that's partly where the name MEL comes from. The other part of the name comes from my grandmother's initials. Below that, we have, I think we've got, I have to check, because my eyesight's not that good. I was out drinking with Dom last night. I've got a couple of diodes. They're Xeon diodes, which I'll talk about in a minute. I've got a capacitor, another diode, another capacitor. On the bottom, we've got a row of resistors. And then right at the end, we've got LED 1 and 2. And LED 2 is just a power light. LED 1 is a user programmable light. So Again, when starting to play around with USB, you may find that you want to get some sort of feedback in the hardware, and the whole point of that LED1 is to provide a way of providing that feedback. All of this stuff is pretty cheap. If I was ever to release this as a final product, it would probably retail at about £5. However, it's going to be given away for free at 44Com. So, let me have a look at some of this here. Let me start with the breadboard prototype. So when you're designing a circuit, has anybody here ever designed hardware before? Awesome, guys. So when you're designing a circuit, what you'll commonly find is that there's a type of prototyping called breadboarding, which you look something like this. And this was my very first implementation of the MEL, and you can see there's a couple of Zenas, there's a couple of resistors, there's the chip, and there's a little USB connector. Now, USB as a standard is a steaming pile of dog turd. From an electrical perspective, it's a royal pain in the backside. Compared to other buses, it's like the red-headed stepchild. And the reason for this is that the voltage fluctuates, the current fluctuates, it's a nightmare. So when you have a circuit and you want to interface over USB, you have to regulate current, voltage, all kinds of things. And there's the right way to do this, which would be to use something like a linear switching regulator that will provide you with a voltage. And then there's the cheap way to do it, which is to take a couple of Zener diodes and drop everything down to 3.6 volts. The even cheaper way still is to go and get some red LEDs and use them as diodes to go and replace the Zeners to have a forward drop of about 2.2 volts out of the 5 volts coming in. That presents a whole bunch of problems, many of which I encountered, and that's why there aren't 2 LEDs there. I wanted to try and make the parts for the MEL as few as possible. I really wanted it to be something that anybody can put together in about 20 minutes. And I tried to get away with not using as much kit as I could. So the Zeners are needed, otherwise you run the risk of frying the USB host. Then you need a third diode on the VCC pin to stop frying the USB host. Many USB hubs gave their lives for this project. Not shown here are a pair of capacitors, which you also need for smoothing out current and voltage fluctuations. Without that, you run the risk of nuking the board. Many AT-Tiny chips also sacrificed their lives. But when it came to actually building the PCB, there's a different story. I learned from my mistakes, and most importantly, learned how to create new ones. Has anybody here ever used a thing called KiCad? Yeah? You poor, poor souls. I tried, but the learning curve is just, it was getting in the way of actually doing stuff in a reasonable time frame. That's not a good prize. Let me see if I can... There we go. Let's start with the schematic, shall we? In fact, yeah. There we go. So this is a design schematic, and for anybody who's never seen one of these before, this is basically a way of saying how the board is pinned together. Anyone here believe in magic? You should believe in magic, because we live in a world where things think using poison sand and tell the time by vibrating crystals. So what we have in here is we've got our smoothing capacitors that weren't on the breadboard, that cause no ends of problems with things just going puff, and not in a good way. We have our USB over at the top there, and what the USB does is you can see we've got a ground, which is the ground signal. We have a 5 volt, which is VCC, and there's a diode to stop things from going back in. We have a USB-M and USB-P. Now, they're commonly referred to as D plus and D minus, but many people who've built similar boards refer to them as M and P, so I thought I'd go with convention for this sort of board. You've got the 2 Zeners, which go to ground, and again, that's to stop stuff from going where it shouldn't and to smooth things out. We've got 2 resistors to work on smoothing some other bits out and just keeping things calm. We hit the AT-Tiny, which does all of our hard work. And then we have, coming out from the pins, we have LED1 and LED2 with current limiting resistors on the way. And then when it comes to it, we have if I switch to board view, there we go. Then we have the board. And the goal is to make something that you can fit in a credit card, credit card slot on a wallet. Unfortunately, because of the capacitors that I'm using, when you assemble it, it's probably not going to work well in your wallet. But it's still a nifty little size, and it's very much a work in progress. Now, what we have to do from that schematic to the board is we have to lay all the parts on the board, and then we have to wire the parts together. And the way that we wire these things together is we put tracks on the board. So you can see that we have this card edge here, and the reason that we have the USB PCB connector on the card is that it saves about £2. Well, between 20 pence and £2, depending on how you look at it. But that connects to the USB. You can see that there's lines coming down that go into the different components on the board. And ultimately, you've got this 6-pin header at the top, which will be replaced with an 8-pin header, hopefully, for the final version. I made the big mistake of not documenting which pin is which. Which is, no, it's a bit crap, really. Because we're connecting directly to the USB connector, the board has to be an unusual thickness. It has to be 2.54 millimeters thick, or as my American friends would call it, 0.1 of an inch. The strip of wires can be used to go and put your own things in if you want, but I'm unsure as to whether or not they're going to be useful, as they'll be bound to earth on the other side. There's also a risk that the solder mask will corrode over time where the PCB connector is. So as you put things in and out, things will start to fall apart. I'm not really selling this very well. But basically as well, because we're doing this on the board, what will happen is if you plug this directly into a computer, a lot of the time it won't work. And that's because, again, USB is a steaming pile of donkey turd. It's really a ghetto bus, because this is a gross abuse of the specs, but lots of USB ports on devices are actually not standard. Like MacBooks, for example, have far more recessed ports than they should be, so when this gets plugged into a Mac, the contacts don't actually reach where they should. So the way around this is to use a USB extension cable, and again, it's more for testing than for general purpose, actual evil things. So let me see. So, as with Blue Peter, here's one I made earlier. Let me show you how it's programmed. Right. So there are several things that we need to do to get this to work and to actually start hacking USB with it. The first thing that we need to do is that we need to go and install the Arduino IDE. The second thing is we need to go and add support for the DigiSpark, because this is in DigiSpark mode. We need to create an in-system programmer, which is just a simple SPI type circuit that we can flash a bootloader onto. We need to then write our code, possibly drink some tea, swear at the code, make it compile, and then we can upload it and have some hackety-hack fun and games. So I'll just show you how to set this up. Let me bring that up there. Okay, so all we do is we go into Preferences, and there's a set of URLs for additional boards. And we want to add the Digistump URL, which you can see here. Then all we need to do is go to the Boards Manager and install the Digistump support. And from that point on, we can program this as a DigiSpark. Now, in order to make this work as a Trinket, you have to install the Trinket bootloader. In order to make it work as a DigiSpark, we have to install a DigiSpark bootloader. DigiSpark uses a common bootloader called Micronucleus, and I will show you how to install Micronucleus. There we go. Oakley dokley. All right. So we've got a hex file, and then what we use is we use a tool called AVRDude. We use the in-system circuit programming from to basically flash the bootloader on, and then we can start uploading it as though it's almost a normal Arduino. In order to get this up and running, I'll just switch over. Let's build an ISP circuit. Now, there are two ways we can do this. We can use a proper ISP programmer, or we can use an Arduino. I have lots of Arduinos, so I don't mind killing them. I'm just going to show you what that circuit looks like and what these AT-Tinies look like. Hopefully. Yep, okay. Unfortunately, you can't really see the text that says what the chips are, but on each of these chips, there's a little circle on one side, and that signifies pin 0 or pin 1, depending on how you count. Just move over to here. Get down to 1.1. Yep. So you've got pin 1 in AVR parlance in the top left, and that contains the heck? Okay. Yeah, that's the reset pin. Then we have pin 4. So I guess if we start from the top left, yeah. So if you look at the top left there, you can see pin 1, pin 4, which is the ground, pin 5, which is on the bottom right, which is PB0. A lot of people using AVRs will refer to this as pin 0, but on the physical layout, it's pin 5. So I'm just going to refer to it as PB0. PB1 going up, and PB2, and then VCC at the top right, so anti-clockwise. It's a simple circuit to set up. It's reasonably well documented. And then all you need to do is, when you're ready, just, there we go, straighten the legs out of this bad boy. And we just pop our chip on the board. Yep. So we've got the chip on the board. You see the legs match up. Make sure I've got it the right way around. Looks like nothing's going to go zap. Fingers crossed. No smoke, we're winning. Okay, right, so I'm going to cheat a little bit by looking at my history. And then switch back over. All right, let me embiggen this for you. All right, so this friendly looking command line is all you need to flash the bootloader. There we go. And basically, I'll just walk through what that's doing. So effectively, we're saying that we're going to run AVR Dude, which is a programming tool with a specific COM file with lots of verbosity. We're programming an AT-Tiny85 chip. We are going to use this particular serial port. We want to set a baud rate of 19200 baud. And then we're going to set these fuse values, and then we're going to upload the micronucleus bootloader. Now, the fuse values, there's 3 fuses that you need to set on an AVR. There's the low fuse, high fuse, and extended fuse, and they configure the AVR microcontroller. So the DigiSpark has one set of fuse settings, Trinket has another. If you're programming a raw AT-Tiny, you'll set your own based on what you need. And what we're setting is low fuse OXE1, high fuse OXDD, E fuse OXFE. And in English, what that means is that we're setting the brownout detection to brownout at 2.7 volts. We're enabling SPI-based download, which we need in order to upload the bootloader. We are enabling self-programming, which means that the chip can be rewritten again and again. We're disabling reset, so we lose a pin in the process, but it allows us to reprogram over USB. And then we're going to set the internal PLL clock to run at 16.5 megahertz. So if I run this and the demo gods are smiling. All right, lots of stuff flashing up on the screen, and what that's doing is it's uploading the micronucleus hex and setting the fuses to the values that we need. So if we were going to do something in the wild with this, let's say a practical application of this would be you want to create a device to go and do hit attacks but the MEL's quite large, so you want a smaller thing. You can recreate that circuit, and all of this is going to be publicly available, and create a smaller board that fits the, the format that you want. You can then go and set the fuses so that the header text can't be reprogrammed and can't be read from the chip. So no one could pull the chip out and see what was actually on there. I mean, hypothetically they could, but without scraping the top off and photographing the die and doing some weird and wacky things, it's not going to happen. So now that we've got the fuses on, let's see if we can get a basic blinker chip working. So I'm going to switch this bit off here, and I think I need to switch back over. Pull this out. There's my clips. There we go. Now, if I put this here, can anyone see the notch about there on the dips? On the dip there. So if you can't, that's basically, that tells you which way up the chip's meant to be. So you want that notch on the top right. Let me see if I can make this a bit bigger for you. No, I guess not. But basically you want the notch on the top right to go in. And I'm doing this with my hands, which you shouldn't really do, but these chips are about 50 pence each. So if it goes wrong, I'll just get another one. There we go. All right. So now we've got our chip back in, and is it the right way up? It's the right way up. I'll then go and get this. There we go. Okay. Now I've got my USB plugged in. Next thing to do is to I'm just going to bring up a Windows VM. All right. Flip this back over. Okay, let me just see if I can zoom in on the code. I might not be able to. No, so I'm sorry there. I don't. Oh, all right. Okay, thanks. This is font size. Make it 16. There we go. So this is a piece of code from the DigiSpark. And the basic premise of running this is that if a piece of code written specifically for the DigiSpark works, then we know that the board is working in DigiSpark mode. The way that what this does is it basically blinks, so it puts the LED on for 1,000 milliseconds and then off for 1,000 milliseconds. And in the hardware world, this is pretty much hello world. So it's not really going to be a very impressive demo, possibly less if it doesn't work. But it is going to be a demo. So I'm going to flip this back over to the hardware because you don't really need me to just hit the compile button. And then pop that here. It's going to tell me to connect the device. So now I flip the power on here. And there we go. That's going to start it. We can see the blinking. It's not as impressive as a hash prompt maybe, but it's a start. So now that we've got the blinking up and running, let's see if we can do something interesting with it. So USB HID devices work on the basis of having a particular type of, at the software level, there's a human interface device profile, and there are different, or class, and there are different subclasses of device. The most commonly used device classes are keyboard and mouse. But there are also things like joystick, there are also things like tablet, there's also things like MIDI. And the way that they work is you define what types of USB report are going to be sent between the host and the guest, and then you create a communication protocol for that. And part of the reason to build this is to give people at 44Con something very quick and easy that they can start doing, keyboard attacks with, but also to encourage people to try and do things that are a little more wacky. So, for example, it would be perfectly feasible to go and take one of these and turn it into a USB fuzzer for a particular subclass of profiles. Something that I did on Wednesday was just to iterate through several things, and then my Windows 10 host just went and balked. So there's probably something interesting there, what I don't know. But being able to go and send those duff reports and corrupt reports allows you to go and test the drivers on the host and the implementation on the host. I wrote a thing a while ago to brute force safes because I was staying in a hotel where somebody foolishly had a USB port on the outside of the safe. And lo and behold, when I connected a keyboard to it and typed in numbers, the numbers came up. So I just wrote a 4-digit brute forcer for it, and it ran while I went down to the bar for a beer, and a few hours later I came back and forgot about it, and I woke up the next morning and the safe was unlocked. But let's see if we can get something a little more interesting going on, and we'll just demo a basic, very simple, very stupid hit attack. So I'll switch that off there. As we're not going to use blinking lights, I'll switch back. And go. All right. Okay. So when I hit upload, what it will do is it will compile and then it will upload. Now, because of the way the micronucleus bootloader works and because of the way the fuses are set, when you power this thing up, there's a 5-second delay before it will do something. And in that 5 seconds, it's waiting for stuff to be uploaded for this. And the reason for this is that while the AT-Tiny has the ability to impersonate any protocol at all, it does not come with hardware serial support. You can implement software serial, but there's no actual hardware UART on there. So I'm going to hit compile and pop this in, and I don't think you'll be able to see it, but it's saying running Digispark uploader, plug-in device now, so we'll switch this on, connect to Mac. It's already, let me just pause that for a moment. All right, that's uploaded now, which is great. So now I'll switch back over to the VM. If I just go, it's not that I don't trust the Wi-Fi in here or any of you guys, it's just that this is a place of wretched villainy. And okay, no, I don't. I really don't want to do that. Okay. Just have a quick check to make sure that Tinternet works. Okay, that looks like that all works there. Okay. All right, so we'll switch this on now and connect to Windows. Okay, I think that's going to take its time. Okay, wants to play an advert first. Screw you, YouTube. All right. So there you go. Not just for people pulling things apart. So so now that we're no strangers to hardware hacking, you know the rules and so do I. One of the obvious things to do would be to go and, has anybody here ever heard of PowerSploit or the PowerShell Mafia stuff? So the obvious thing would be to go and take the PowerShell Mafia GitHub, stick it up on a server somewhere, and write a head payload that will then automatically use PowerShell to download, say something like the invoke shellcode function over IEX, download the string, and then invoke shellcode to go and set up an interpreter and then go back. And I was planning on getting that done, but instead I went out on the beer last night. But you can do it, it's not hard, it's the same sort of thing that you do with the USB rubber ducky. At 44Con, I'm hoping that what we'll be able to do is, there's some code that's particularly shonky that I'm writing that will allow you to translate ducky script into Digispark code. So you can just go, all my ducky script stuff, drop that on there to get you up and running. And the whole point of this is just to get you something that works in, under 20 minutes and allows you to start with hardware hacking where you can say, actually, I put this thing together, I soldered it all myself, there's nothing special to this stuff. And then to start exploring with other head things and seeing if you could do things that maybe perhaps bring up something like Paint and draw a logo of whatever your favorite thing is, or just, I don't know, penises or something, whatever. But to basically have a play with head systems and have a bit of fun with it. And basically, we're going to give these away at 44Con, and then we'll open source all of the hardware and all of the software. So if you're not able to come to 44Con, you'll be able to go and build your own and get your own made somewhere like OSH Park or Ragworm. And if you are coming along, for the first year, we'll be able to go and give you all of the stuff and all of the bits to put it together. And if we can find the space, we're going to run some workshops as well to assemble these and do some things with them. So that's pretty much the entire thing for me. So yeah, I foolishly went and printed out the code listings that I was putting in anyway, so I don't have anything else there. Any questions? Gentleman up front. Not at the moment, and not that version. So after 44Con, there will probably be changes to it, and once I've got a bit more code for it, I plan to go and make them available generally for sale next year, and it will probably be in the 2 for £10 bracket, which I know is a big investment to make, but I'm trying to build something that will be a more general purpose computing device, and with this as the prototype for that, realistically, it's more about getting feedback on it. I want to make sure that there's a full set of software and instructions before I just start selling these things, because otherwise people are just going to stick them in drawers. I'd rather that people stuck well-documented things in drawers, like Raspberry Pis, than things that were not supported. Any other questions? Gentleman over there?
You were saying that it supports different bootloaders in the chip, so you want Digispark. Is there a reason you choose one over the other? Is the Digispark better for certain classes of devices?
So the Digispark has a set of functions which I can show you here. So you can see this DigiKeyboard, and it's just a really easy way of not having to write your own keyboard library. If you wanted to go and use this to do other things, you might find that the Trinket firmware is better, particularly if you want to interface with things like NeoPixels or things that are developed by Adafruit. But then you're potentially going to have to use a different keyboard library if you want to do keyboard stuff. I mean, to think of it in terms of the non-security stuff you can do, you can plug a thermometer into this, and you could have it go and communicate over USB and, literally write an email and send it to you telling you what the temperature is, or, have like Moss from the IT crowd, when the temperature goes over a certain level, send me an email saying, "Fire!" exclamation mark. Fire! Exclamation mark. So any of those things. Thanks. Any other questions? Sorry? I can't. I'm disabled. All right. Sorry, gentleman over there. Yes. Yeah, so the actual Digispark is cheaper, but it's all surface mount. And you can get cheap Chinese versions of it for about in the order of around £1. But you don't solder it yourself, you don't flash your own bootloader on it, you don't do all the learning stuff. So for the basic hit attack stuff, that's great. That fits in a thumb drive brilliantly. But you've still got that USB PCB bit on the end. The thing about this is that if you build a head circuit with this, and because all the components are freely available, if you want to build your own thumb drive, if you're okay with using something like Eagle or, God forbid, KiCad, you could go and design your own PCB that will fit in there. And most people have already done this with similar types of boards. And you can program everything on this and then just pull the chip out and put it into the other circuit. And it should all work fine. All right. Any other questions before I step away and let the next person talk? Oh, all right. Well, thank you very much.